What I've developed is a UHF RFID reader, which is just as flexible because it's entirely software defined. And this was done at the University of Washington with my advisor, David Weatherall. So this Gen 2 protocol has really driven the emergence of all of these RFID devices, these RFID applications, and the industry is booming. And it's very good at its job, which is identifying tags in a population of unknown size. But as we discussed earlier, if you're trying to do anything else, Gen 2 isn't always really the best fit. So as these new devices come on the market, like the WISP and then also the US passport card, what you're trying to get out of the protocol changes. Now it's not actually reading an unknown set of tags, it's reading maybe sensor data from a known set of tags, or else reading the ID from a identification document, where you would like to have some sort of crypto on top of that to make it more privacy preserving. They didn't worry about that too much in the first place, but I think everybody would like it in future versions. So there's no shortage of proposals for what you could do if you had flexibility over the protocol. So just looking at Gen 2 and making it better, there's been a lot of work at that kind of singulation process, the MAC protocol. So either refining the frame size or estimating the number of tags so you know exactly how many slots to have in your frame. There's also been people looking at CDMA-based RFID systems. So if you have many tags are talking at once, if you use CDMA, you can now decode all of their responses at the same time, which makes a lot of sense. And also some work that we looked previously, just how tweaking some of the Gen 2 file layer parameters could actually increase performance. There's obviously a lot of interest in privacy and security. We have a whole session coming up later in the afternoon on this topic. And one thing that I've been interested in most recently is protocols really suited for these sensing applications, especially for trickle charge devices like the WISP. What should these protocols look like to be high data rate, but also make sure that the WISPs don't waste, or make sure the devices don't waste a lot of energy. But the problem is that there's no tools to experimentally validate any of these proposals. Everything's either been done by analysis or in simulation in some cases, but very few cases. So this is just kind of what the situation looks like. Both the tag and the reader are inflexible. Everything's either behind proprietary firmware or just done in hardware. The WISP has really gone a long ways towards changing this. And what we've done now is kind of given us that same level of flexibility on the RFID reader side too. So what we did is developed a flexible software-defined RFID reader. It's based on relatively cheap, about $1,000 open source hardware, and the file layer and the MAC layer is done entirely in software. So it's actually pretty easy to make protocol changes at either of those layers. And we actually have gotten the performance to a point where you can communicate with standard RFID tags, and then also the WISPs, which, because of the timing requirements, is actually a little bit easier. So the platform itself, we use the Universal Software Radio Peripheral. So what this is you can just buy it off, just order it on their website. It's about $1,000, maybe $2,000 once you get all the bells and whistles. It's a general purpose software radio. It's not targeted towards RFID. It's not targeted toward any application in particular. So the way that this works is it has daughter boards, which just down convert different frequencies depending what daughter board you're using, down to baseband. And then there's a ADC on the USRP, which just samples it and just transfers that raw IQ data over a USB bus to the PC. And then the transmit side looks pretty much the same. You just send samples, and that takes care of up-converting it and transmitting it. But of course, you need to do the signal processing somehow. So this is done using the GNU Radio Toolkit, which is free and open source, and this was developed specifically for use with the USRP. Everything's written in C++, and then use a Python program to take your C++ signal processing blocks and tie them all together into a full flow graph, which will implement your signal processing. And then there's a GNU Radio runtime scheduler, which deals with taking samples from the output of one block and moving them into the input of the next block, and takes care of all of that for you. So all you have to do is write the signal processing code. So our contribution was we developed signal processing blocks that implement the Gen 2 protocol. And it's all in software, so it's easy to change. So when we first started out on this project, we saw 3 challenges. We didn't really know how it was which of these was really going to be the one that tripped us up. The first was powering the tag. So the USRP that I used for the data that I'll show had a 75 milliwatt output. You can actually get it up to 500 milliwatt output. But also, if you wanted to put an external amplifier on, you could actually increase the output as much as you want. You probably have to do some other tricks on the front end, because one of the main problems is if you transmit on high input power, that's going to get fed back into your receive chain, which increases the noise. But it turned out that we could actually read up to about 8 feet, which is enough for, doing kind of sanity checks and protocol development. Not for deploying a full application. That's the next step. So then we then thought that decoding the low power tag responses, because you're getting a very small signal reflected back from the tag, was going to be a problem. But that just turned out actually learning the standard RF techniques that all RFID readers use. So it's not that interesting. I'm not going to talk about it, but I'll have a link to a paper at the end, so if you want any more details. What turned out to really be a problem was achieving low latency. So because you're taking the samples, going over a USB bus into a general purpose CPU, doing the signal processing in user space and sending it back, the latency is really high. And we need low latency because there's timing constraints for standard RFID tags. And if you want your protocols to be realistic when you're using the WISP, we actually need to have pretty tight timing constraints. So this is what I'm going to talk about for most of the talk. So the timing constraints I'm talking about in Gen 2, the one that's there's a number of them. This is, if you remember, there's the query and the RN16 and the ACK. So this is kind of the same MAC protocol that I showed earlier. The timing constraint we're worried about is the time from the end of the tag response to the start of the reader response. So if we don't send this ACK within this time of T2, the tag will just entirely ignore it. So you have to hit that timing bound if you want to work with standard tags. And the exact duration of the T2 depends on the uplink frequency I talked about before. There's different ones. So for the WISP, to hit that timing requirement, we need an 80 microsecond turnaround. The WISP doesn't really care whether you hit the timing bound, so it's not such a big deal. But the standard tags do. So the 40 kilohertz case is the lowest frequency uplink, which gives us a 500 microsecond window to hit. Unfortunately, some previous work using the USRP for a full transceiver had round trip times well above 10 milliseconds. So we were orders of magnitude off. And just to get back to even if you want to use the WISP, you want them to be realistic. A query from the impinge reader to the WISP is about 1 millisecond long. So if you send a 1 millisecond command and then you have to wait 10 milliseconds for your next command, your protocol's going to look kind of ridiculous. So the source of latency, this is the block diagram of the system. So the USRP is kind of over to the right and has fixed size buffers, transmits the data over the USB to the host. And the host, that kernel section, the kernel item on the diagram, is in the Linux kernel, where the other two, the fast USB library, is part of GNU Radio, which interfaces with the Linux kernel, and the source and sink are the entrance and exit points of your signal processing graph. So there's three major sources of latency in the receive chain. The first is how long the data stays on the USRP before it's transmitted over to the host. And since there's these fixed size buffers, if you have high sample rate, those buffers fill very quickly and get transmitted very quickly. If you have low sample rates, it takes a long time for those to fill, so the data will only be transmitted. You'll get more data at once, but the latency is increased. The second one is how long does your data sit in the Linux kernel before you pull it out. So you have some flexibility about how much buffering you have in the kernel, but if you have it too small, you're going to have overruns, so you lose a bunch of data. So they can't be too small, but if they're too big, then it increases latency. And the last source of latency is how long it takes you to process your signal. So if you have high sample rates to get the samples through the buffers, now you have more samples to process in your signal processing graph, which increases your processing time, so now you have latency there. So there's kind of these trade-offs about, how can we actually reduce the latency across the whole system? I'm not going to go too much into the exact details. Again, you can look at the paper. One, we moved some of the functionality to the FPGA, so we reduced our transmit latency. Second one is we re-engineered how the USB interface works. So instead of having these large fixed-size buffers, which was causing GNU Radio to block and wait until samples came in, so blocking was just wasting time, we have rate matching where when the GNU Radio comes back and asks for samples, it just takes whatever samples are there, and then it begins processing. So what you end up doing is actually matching how much your signal processing time takes. You'll pull in just how many samples it takes to process for that amount of time. The last one is protocol-aware scheduling. So if you start decoding part of a tag response, you know exactly how many samples you need until the end of that response. So instead of pulling in a whole